Hello, everyone. Good to see you. So exciting. Data-driven discovery. Oh, this is my favorite topic. And then organizer just dropped this news that I'm supposed to do elevator pitch. Okay, so I'm Tomoko Matsuo from CU Boulder. I teach in the aerospace department about data analytics. And then I'm also affiliated with applied math. So I studied data science before data science was a thing. So that's my pitch. So I have learned really hard way. And so it's really exciting to see the world has changed this much, that NASA, Heliophysics, embracing data science heads on. And then look at you. You are spending 10 days, nice time in summer, in this room at the HAO, right? Learning about this. So I don't know if that constitutes a pitch, but I'm excited. And then this is the things I do, what I have been doing. And then also data is something that I love to explore. And that is a topic of my lecture, examples and emerging topics of exploratory data analysis. So I'm asked to sort of basically showcase some of the examples of analysis techniques that you've been learning in the form, primarily, I think, in the form of equations and then theory. So I'm going to show how that might work. And so one thing I want to tell you is I was exactly where you were about 20 years ago, right? And then, so one story I want to share is that when I was finishing up my PhD, I told you there's no such thing like data science. So, but I was interested in. And then I ended up leaving the field of space physics. And I jumped in the statistics. That's where basically learning techniques were formally sort of investigated and applied. So I did postdoc among statisticians. And then that was interesting, was a hard way of learning, right? Data science. But what happened was that around the time the world has changed, computer resource got so expensive, and then there's sort of era of big data came, right? And then so world has changed. So if you're actually thinking about the overwhelmed or you're not really sure, exactly that's how I was when I was a graduate student. Whoa, what's going on, right? And then one of the things you can have control is to do things like that, right? Learn new things. But also, world will change, and then changing dramatically right now. And then so for me, it worked out. And then I landed on a faculty job after taking that detour. So that's a mini story that I wanted to share. Okay, so coming back to one of the things, how world has changed. So on Thursday or Friday or so, you have attended a lecture about Enrico and on, I think, about examples of machine learning in heliophysics. And then he mentioned something like a fourth pillar of science method, scientific approach. So because of that revolution, data science is recognized as scientific sort of method to discover. So discover knowledge, discover understanding of this heliophysics that we are all after. So what we are doing here is an application of data science methodologies. We're transforming data into scientific knowledge. And so let's step back. So in a traditional sense, there are sort of two different main, well, so there's four different ways, but also traditionally, when you think about it, there are two sort of classic paradigms of scientific inquiry. One is starting from observations and then extract the pattern, and then build hypothesis, and then theorize. So this is an inductive method, inductive approach, right? And then so basically you are learning to be a good data detective. What's going on, right? Start from data. And then there's another paradigm, second paradigm, okay? So deductionist. So you start from theory, axiom, right? Law of physics, you know that. And then hypothesize, apply to sun, magnetosphere, right? And then you go out. So those are the really classic sort of trajectory of space physics has taken, right? So send a probe and then see if they are magnetopoles, right? And like, for example, that's really exciting, right? So that's kind of how it goes. And then confirm with observations, probe, data set. So what's going on here is that, let's hold. Want to go back? Okay, so here we go. So what's happening right now is because of computing power and then availability of big data, right? So we are basically having a bit hybrid approach. And then we have something called fourth pillar of scientific reasoning or approach, which is data science. Okay, so, and then zoom into exact sort of more topic that I'm asked to cover is the application of primarily unsupervised learning technique to data sets, right? So in machine learning, you could actually, techniques are categorized into two types, supervised learning techniques and unsupervised techniques. Yeah, you're nodding, so you know what differentiates. So type of data that required to use supervised learning techniques are labeled data sets. And then in practice, it's really powerful. Well, it's powerful methods, but in practice, it's really difficult to get hands on really good labeled data set. Have you experienced it? Have you experienced yourself? There's some nods. So it's hard, right? And often in our field, we have to do it yourself. So as a graduate student, I was also given a bag of data, maybe not that big of data sets that you are given to or have access to. And then of course we didn't really have that level data set. So in that case, a way to go is unsupervised learning techniques. And that's kind of what you actually find yourself. First thing you're gonna do is, oh my goodness, there are hundreds of different approaches. And then you have all the Python toolkits you can install, and then you can actually do it pretty fast, pretty quickly. But on the other hand, there's also, I believe that you'll be encountered with this dilemma or question, which way to go? It's overwhelming. Have you felt like you're overwhelmed? You're really not sure? Okay, yeah, you are. That's where you're probably supposed to feel. And then I'm validating your feeling. Okay, good. If you're thinking of solving your problem seriously, you probably should, that's kind of natural state. Okay, which way to go? So I'll tell you. So I told you, I've done this in a really hard way. So hope I could share something. And then this is before doing anything, just you got to know your data. Know your data, yeah? And then, so unsupervised techniques will give you really systematic way of exploring the data sets, get to know your data sets, what kind of issues, challenges are hidden in the data, right? So, okay, so it's easy easier, right? I'm not saying easy, easier than the time that I was exposed to this problem. There are lots of toolkits. You have access to larger data set, but just do check the data, right? First, know your data. So remember garbage in, garbage out. Have you heard about this? Yeah, you could spend hours applying fancy techniques, advanced techniques, and then come to writing a paper or going to your advisor's office and oops, right? Yeah, so do this, even though end game is maybe, deep learning, neural network, do that, just open it, try it, and then apply unsupervised technique because it's a kind of threshold is lower, right? Because it doesn't require labeled data sets. And then you learn tons of things. Okay, so today I want to cover clustering. So you've seen in the formally introduced, K-means clustering is formally introduced on Saturday's lecture. Yeah, and then you know in theory, and then so I want to cover that applications and some examples, and then more kind of like a practical point of view, like what you might need to do, or if you haven't done it before, or even if you have done it, hopefully there's something that you find it useful. And then, so you have learned a principal component or dimensional reduction approach, right? So you have learned the background, or theory behind it. And then that is PCA, for example, or a kernel version of it, or Gaussian mixture model, that kind of thing you have learned is actually really to be used as a feature engineering steps of deep learning, right? So you don't need to, I'll come to that features that you can feed into your neural network. So unsupervised methods could be used that way. So you don't need to pick, oh, I have to use, I want to use unsupervised method. Well, supervised method, you can actually mix and match to get that best outcome. And then, so also I'm gonna talk about different types of applications in heliophysics. So two examples that I'm gonna share is solar wind classification examples. And then I'm gonna share from my own work its application to thermosphere and ionosphere. So there are tons of other applications. But I'm here to connect the dots between equations that you're exposed to, you understood, hopefully, the theoretical backing of that, each method. I know it's, and then how can be used to actual data analysis. Yeah, so I'm gonna check my time. I don't, I know you're waiting for lunch after this, so get there. Okay, so let me begin with clustering. And then clustering refers to a broad range of techniques that it's designed to find subgroups or clusters within a data set. And then if clustering technique is applied to, for example, multi-spectrum data. So this example is a really super simple example, like a RGB image, so 3 colors, right? So that is basically features. So 3 colors, that works as a features, right? And then you could apply, K means clustering. Actually, that's what it is. So it's K. What do you know about K? That the number of classes, but how are you gonna go about picking K? You just have to choose. So that is basically downside of it. And I'm gonna kind of go over some practical examples or approach to bring in a bit more objectivity in choosing K. So here's an example of K code 19. K means clustering applied to feature number D. D, I'm gonna use D in my lecture note. So there's 3 features, right? And then it becomes a segmentation image, right? So this is classification, clustering, and then examples, they're basically the same. Okay, K means clustering. So you've seen this before, maybe it's slightly different, but then what you're doing is to assign every single data point, right? So in this case, in our previous examples, those each pixels on the image is a data point. And then you wanna, data, and then you wanna basically classify each pixel to different groups. And what you are doing is that if you look at the objective function, you are really trying to minimize that within a cluster variation. So so in the previous example, there are 19, right? So 19 classes, right? So within the 19 classes, within class, the variations are small. So that's what those objective functions let you do. So that's basically formal presentation. Okay, and then you learn, I think EM method or expectation maximization method. So that's one way to implement k-means clustering. And then what you do is you set up an objective function like this, and then what is actually doing, that's exactly this. What if you minimize this objective function, you're gonna achieve clustering of data that minimize within the cluster variability. And then most common measure of similarity is Euclidean distance. Right? So here in the previous example, there's three-dimensional data sets, D equals 3, right? So Euclidean distance can be defined that way. But you could have a lot higher dimension as well, and then you don't need to pick Euclidean distance. And then, so those are the things that you could open the hood if you're using Python or any other software package. You don't need to say, oh, you could change it, right? So so basically I'm giving pep talk to all the theoretical lectures that are given by the Farzad, and then it pays off, right? That is an edge, right? That is payoff for you to decide to come here, to sit in this dark or actually bright room, but cold room, instead maybe hiking in the Rockies, right? Okay, so you understand what's going on, so that you can tweak the stuff, right? It's options. You open that software options, and then you don't, anyhow. So that's Euclidean distance is one example, and then you could do this iterative implementation of maximization, maximal likelihood, as you learn, and then you could get to that sort of like over time, over the iterative loop, minimum centroid and cluster assignment, right? So you are learning, in this case, cluster assignment R, right? And then centroid location for the which cluster, right? So those were the two parameters you've been learning through this. Okay, and then I've seen this plots on a Saturday lecture. So this is Christopher James Bishop's textbook. So it's actually what was applied is, so this is a really famous Old Faithful data set that it's around. So N stands for number of trials. So there's 272 samples. D equal 2, right? So dimension, the feature space is 2. So you are minimizing, I think, features are time between eruptions, and then the sort of height of, I forgot. So the size of basically eruption. So those are the two those are the features. Do you understand? So when you are given a bag of data, before you're doing a clustering, think about how many samples you have, N, and then what are the features, right? N, D, and K. What is that? You have to pick from thin air. Okay, let's do 2. And that wasn't really good, was good for the example. So anyhow, so you've seen this plots before, and then you do this expectation, maximization steps, and then you achieve minimum. Is it global minimum or local minimum? You learn it on Saturday. Can that global minimum, do you understand the difference? Right, you are experts, right? Exactly, yeah. So it's it's a difficult. So it can get stuck. It can get stuck in a local minimum, and it depends on the initial cluster assignments and so forth. And then how to pick K, that's another thing. So when you start applying your method or machine learning techniques, there's lots of things you need to think about. But that is where you can distinguish yourself, right? Because everybody can download. Bug of data is available from NASA, right? Right? Okay, so just really bring your mind and then think about what's going on. So this is how that cost function get minimized in this simple example. Okay, and then so there's also a question on where to stop. Are we, because you might get stuck in a local minima, so keep going, right? Burning more GPU, right? But then you could check the objective function, right? And then check the elbow. That's right. I mean, that is also heuristic, but you know, yeah, because there's a default setting, stopping condition when you start using k-means, for example, any kinds of iterative methods. But you don't need to accept the default, right? If you know how to open the hood. Okay. So recap. So essentially, you're really what you're doing is that within the cluster variations, you try to minimize that, and then the algorithm is set. If it's working, it should decrease over time, right? Over the duration. K-means algorithm has tendency to stuck in the local minima, check it. And then, well, you really need to probably try many different trials. Start with different initial cluster, for example, assignments. You're gonna get the different answers, right? And then, so that's something that you need to check when you apply. And then the problem of selecting K, number of cluster, is far from simple. Okay, and then I'm gonna move to first example that I'm gonna introduce, solar wind classification example. And then within it, I found really nice application of something called cross validation. And that is a really go-to method. Especially if you're really closer to data sets, and then something that you could do, not just in this context, but cross-validation. So I'm gonna introduce that as a practical way of knowing, or a practical way of knowing a bit more objectively what is actually, really optimal K. If you're dealing with data, it depends on data you get, right? Answer you get depends on data, right? So that's kind of like constraint you there, but that's really make you a really good practitioner knowing that. Okay, so this is an example that I found in this textbook. Have you seen this textbook? Right? It's a great sort of collection of work in our field, and then it's out there. Machine learning techniques for space weather. I think came out 2018, and then so chapter 16 I just plugged. I pulled out. So I think the reason why I liked it is it's k-means classic application. So you can learn about that, how that is used, and then uses cross-validation to pick K, which is, in my opinion, really good practice. I really want all of you to do that, hopefully, right, after this. And then also what I found interesting is that I think in my field, in our field, there's a sort of, solar wind has been classified by experts. So without using machine learning techniques, the people that all the distinguished scientists have seen this data set many years, came up with classification, sort of decision boundaries based on solar wind speed or composition of plasma, etc. Right? And then those are based on physics, right? And then for machine learning technique practitioners to earn the trust of those established senior scientists, I think we still need to do that. So I think so this paper really showcased that introducing machine learning technique, so strictly learning from data principle, right, without really putting subjective decision boundaries. and then comparing against the expert based expert knowledge-based decision boundaries. And then it happened to correspond pretty well. So you probably need to do that when you actually write your own paper. Look at the older paper, or classic seminal papers in your discipline, and then so that you have to discuss validity of your results. So for that, I think it's a really good chapter to take a look. Okay, SolarWind classification data. So this have this work look at 10 years of ACE data sets spanning 2001 to 2010. Right? And then those are about 500,000, about 10 minutes SolarWind segments. And then, for example, here, so this is not just a sort of basically what I'm saying, expert knowledge-based classification results. Okay, I'm gonna, if I could use this. Here you go. So here you go. So this is a plane of density and then SolarWind speed plane, and then so using speed only classification. So those are the, okay, so speed faster than, what is that, 200, I'm sorry, 500, 450 is categorized as basically fast and slow, right? So this is a slow wind, okay, yeah, okay. And then there are Zawon things. They have classification rules based on composition of plasma, charge state ratios of atomic oxygen ions and carbons, right? And then you can see that it's not just a kind of clear cutoff with respect to SolarWind speed. And then Shu and then Borodsky 2015. So they used expanded basically the features, and then divided the SolarWind into 4 type categories. Okay, so these are expert, traditional way of doing things. Okay, so it's hard to look. Okay, yeah, which one is better? It's just different, right? Okay, so then understandable that we want, because you're the new people, right? You carry this weight of heliophysics, right, on your shoulder. Like let's data tell us the truth, right? Okay, so then so in this paper showcase examples that's shown is that 7-dimensional feature space, right? RGB example, that's 3-dimension. Here, clustering is applied with this 500,000 data set, n equal 500,000, right? About that, and then d equals 7, and that is based on this. Basically, it's called relatively. The features are based on, let's say, raw features that you can derive directly from observations. And then later, I'm gonna explain or introduce. You don't need to do that. You can actually do something called feature engineering. This is one more classic example when you want to do clustering. Okay, got it? Okay, d equals 7, n equal about 500,000, and then we don't know k goal, right? K, it could be, I don't know, 7, 10, 20. So then what I like about this work is that use cross-validation. So this is cross-validation. This is just a simple one-slide introduction, graphical introduction to cross-validation. So cross-validation is used in a different context, but in a nutshell, you divide data sets into, let's say, I use M, usually use k-fold, but it's confusing with the k-means. So let's say you divide into m-fold cross-validation data sets, right? And then in this case, you can see example is 5, right? So entire data set chunked up to 5-fold, and then you train, you set aside that 1-fold for validation. So you train with basically blue. So there's 5 trials in this. in this graphic. And then you train your clustering rules using blue parts of the data sets and then validate with data sets that you haven't used for training, right? It's a sensible thing to do. And then you repeat through this over the different folds, okay? And then you can come up with metric for cross-validation error. In this case, it looks like so basically within cluster variations being summarized over different m-fold, right? And then all the clusters. So that is cross-validation error matrix. And then if you look at this paper later, hopefully, and then so this is one of the results shown. So it's 10-fold, m equal, in this case, 10. So this, all the data sets is data set divided into 10 different folds, and then they went through the k-means clustering, yeah, and then validate against the data that's set aside, and then try different k, starting with 2, 3, 4, and then went all the way to 20, right? It's just that tons of work, right? But only computer get it done quickly. So you can see that. That error, cross-validation error, that definition I've shown just in the previous slide, that it's interesting. Here it's going down. Okay, if I increase k, error gets smaller and smaller. Whoa. But what you're gonna, so here that is a red dots, red cross. And then they tried, I think they randomized the initial cluster assignments. So that's why you could see that there's a bar, right? So it's not, they're not just showing one set of cross validations. They tried it with 20 or some different randomized initial cluster assignments. So quite extensive work. So you can see error is going down, but then you can see, especially if you see the bottom one, the black cross, so that is a error difference in the median, right? So you can see that effort of increasing k is gonna actually have diminishing return. Does it make sense? It's gonna kind of, the curve black cross, curve gonna plateau. So you see there's some, so this is empirical, but it's a bit better than I'm saying like, oh, I like 20, right? So you could do cross-validation to pick. In this case, it's k equals 7 is taken as winner because if you see that cross, like it's just between around 7 and 8, right? Number of clusters, there's no gain by increasing the number of clusters. And that's where I'm gonna stop, right? Okay, got it? So here it goes. So this is the final application results that showcased in presented in this paper. K equals 7, chosen by cross-validation attempt, right? And then D equals 7, right? So those are the features that derive from raw solar wind parameters. And then you can see the results here. So this is it's showing the same clustering results in a different plane. Left-hand side is density and plasma density, and then solar wind velocity plane. Does that make sense? So there's 1, 2, 3, 4, 5, 7, right? 7 clusters, right? And then it's hard to see. Well, hopefully you open that PDF later. And then cluster 3, this is a moment of truth. I don't know, here you go, here. This is cluster 3. And then about 42% is categorized to this cluster 3. And that corresponds to slow solar wind. And then the reason why they could say this is a slow solar wind is that because they actually cross-checked with a traditional expert-based decision boundaries. So it's actually its correspondence is higher. Cluster 3 is is learned from data purely, but it corresponds most to classic slow solar wind. So that's why this is cluster 3 is a slow solar wind. But right, you learn from data. And cluster 4 and 7, 1, 2, 3, 4, where is it? 4 and then 7. So 4, 21% of data get classified as cluster 4, right? And then cluster 7 is just 7%. And then, so this represents colonal hole solar wind. Again, checked against that more traditional expert knowledge-based decision boundary classification methods. So but this is a really thorough attempt of classifying solar wind based on ACE data, and then there's a good correspondence to sort of traditional way of classifying solar wind. But with this, yeah, go ahead. Yeah, what? Yeah. So that's kind of like a moral of this paper, right? Okay, go ahead, ask. Yeah.
Yeah. Yeah, next one. Yeah. So here I'm confused here why the clusters 4 and 7 can't be in one single cluster.
Yeah. You can 4 and 7. So okay, so that's interesting. So the physical interpretation is likely coming from colonal hole. But when you look at this, right, not all solar wind that coming from colonal hole is gonna basically have a phase space, what sort of distribution. Look at the 4 and then 7, has a distinct difference, right? So if you are actually, doesn't make sense. So it's basically data is telling that there's a bit of differences within all the solar wind that likely that coming from colonal hole, but there's a distinct grouping, which is interesting, right? So that's what let you do if you do this. But if you really pre-assign, okay, let's put everything in one bag, you wouldn't know. So that's so why you cannot do it? If you want to pre-assign that, you can do it, but then data is telling a new information. And then scientists need to figure out, right? As a data scientist, at this point, if you only do clustering, that's all you can say, right? And then you have to work with other people more. You have to basically do more. Maybe you have to do regression after clustering. But isn't it neat? That's really great question. Yeah? Thank you. Do you have other? You guys have? Go ahead. You have to pass this box. That's. I think you can throw it. Oh, I see.
On the kind of similar question on the previous slide, where you choose 7, like what makes you choose 7 versus like 6 or 8 or 9? Because it's like kind of a curve. It's not like a sharp change.
I don't. This paper didn't share, but what I could guess is that look at this. So this is the difference. So the red is a pure error for particular number of k, and then this cross is basically reduction in the objective function or error metric between previous number of cluster, right? K and then k minus 1. If this, so what I see is around 7. Well, why not 8? I think you could actually set up yet another objective function or some metric that this difference between error difference gets smaller than something. That is when you want to solve. You don't, yeah, got it?
Yeah, thanks.
But isn't it cool? You can actually make it objective within the data sets you're given. Okay, those are really good questions. You're paying attention. Makes me happy. Okay, let's proceed. Yeah, Nick, they're really good students. Don't you think so? So you know this. Oh, as if we are coordinated, Nick.
I have like a kind of a naive question. So regarding, can you go to the previous slide?
I'm sorry, I'm going.
Yeah. So suppose we have like a ring of data, like a ring of data.
Ring of data.
A ring of data. So and we want to do cluster on that two-dimensional. So suppose it's a two-dimensional data set and it's a ring, right? As you increase the number of cluster, the cross-validation error is going to decrease, right? Because, but then that data set itself is intrinsically not clusterable. So
Fantastic question. So I have next topic
okay.
that I want to introduce. So this is a great. So some of the data sets, so the example is sort of, let's say you plot your data sets and whatever the plane, in this case, solar wind velocity plane or whatever then it looks like a ring. That means nonlinear. The decision boundary won't be like it's not identifiable easily, just like this, right? So it's a, so what do? So you could do feature engineering before you doing a clustering. And I found a paper that actually does that. So I wanna so then I want you to I want that you ask that question later if I manage to explain. So with the great question as a segue to the next topic, so you learned something called, is it okay? So I'm gonna move to the next topic. So I wanna talk about principal component analysis, and then you learned what this entails, and then you probably might have, well, in theory, and then you may probably have done it yourself, right? So PCA is a projection, orthogonal projection of data sets that basically maximize variance of projected data. So that's one interpretation of mathematical interpretation of what that algorithm, what method is about. And then I think you learned, right? There's another way to think about is so this is the example that previous slide, so it really matches with the previous examples, but so you could really think about is one is a maximum variance approach, but the other approach is a least square kind of interpretation of the mathematical sort of algorithm. So that in case that you are minimizing the difference of projected data from that original data sets, and then those are basically equivalent. You learn that, right? You're good? Good? Yeah, so that's that. I just thought. So, okay, so with that, so how in practice, how PCA is implemented, if you download your software, and then I think nowadays called just PCA, right? So you just have to give data matrix, and that's it, do it for you. But what it's doing is that basically eigenvalue decomposition. So what you do is that, okay, because I had to do this, I didn't have those software. I had to do everything by myself, which is good. I learned it. Yes. Right. So what you do is you set up the data sets, right? So you have multi-dimensional data, right? So feature could be 3D, like RGB, like solar wind example, D could be 7, and then it could be, like so many, couple hundreds, right? Like I analyze hyperspectrum image data sets, and then like has like 100 of channels. Could be D equal 100, right? And then but what you are doing is in a discrete space. That's what you're doing. So you're basically maximizing projected variance of the data set. So that's the top equations, and then you that constraint problem that is subject to constraint that the axis or the subspace that you are finding has to be orthogonal, right? So you do that, and then this is basically implemented as eigenvalue decomposition at the bottom, right, shown here. So that's what you're doing. You're looking for eigenvalues, eigenvectors from data, and then how you actually practically do if you don't use the convenient method, that software. So you form covariance, sample error covariance matrix first, right? So you just have to be clear about what you're doing, and that's actually it's good to do it anyway. It tells you that, you know, let's say you have 100 feature space, and then you have 10 samples. Maybe you shouldn't be doing that, right? So covariance, you know, the basically algorithm that you're using, implemented by somebody else, the covariance is ill-conditioned, and then well, it's not. So if feature space is if you don't have sufficient number of samples for the degree of basic freedom or number of features, the covariance itself is not uniquely determined, and in general, it's not determined from discrete samples. But for example, if you want to write yourself, you can actually do the eigenvalue decomposition of sample error covariance, and then you could actually, this is your PCA, and then it's up to you how many eigenvectors that you want to project to. So those are, again, here you could also use cross-validation type of approach to determine how many axes, how many projection number of subspace you might want to pick. Okay, so that's it. I'm sorry, I'm just digressing. Okay, coming back to your question. Well, what you're gonna do if data are not nicely distributed and whatever the feature space that you have. So right-hand axis, okay, so here you go. So this is a kind of like a ring. It's not quite ring, but it's if the data are distributed in their feature space, like a left-hand side, right? And then I could see it in my eyes, right? But it's not easily separable by linear distribution boundary. So then what you do is somebody thought about it. So there's called kernel version of PCA, kernel PCA. So if you're dealing real data sets, and usually those are non-linear, and then so that you might want to check out the kernel version of it, and that's you can find it in Python toolkit. But so what you do is you're gonna project so-called high-dimensional feature space. So that is the right-hand side. So theta is, let's say that so you can think about, so in 2D, this looks like a ring, or like distribution of dots looks non-linear, well, it's not organized the way that easily separable. But let's say you project to 3D space, 4D space, then you kind of, oh, wow, all of a sudden you could see that clear separation of data set as it's shown right-hand side. Theta 1, theta 2 is data transformed to so-called feature space. So at the bottom of the equation is, so that's what that equation, formally, defined how it's defined is, okay, so then you're gonna ask, how am I gonna find the theta? If you knew, this is solve the problem, basically, right? You don't. The kernel, you don't mean, well, it's difficult, and it's almost impossible to find that mapping function, right? So kernel PCA uses something called kernel trick to bypass the really difficult thing of finding this data. So the trick, or the bottom order, I'm just really short. You could have one dedicated lecture on the kernel PCA. So this is the fast version, right? So top one, algorithmically, what you're doing in regular PCA is maximizing the variance of projected data, right? yeah, top, those two. And then kernel version is that instead that you're actually doing the same thing, but it's you dealing with the data that already projected to have this sort of feature space. And then what you pay attention is, so X is a matrix, right? X transpose X, and then theta transpose theta, right? So those are inner product. This is a really good insight. Gets you also a bit of edge above others, because whenever you see inner products, you could actually use this called kernel trick. But what it does is that basically, in a nutshell, this inner product could be represented by so-called kernel function, and then skip over, bypass that step to do that, finding the theta and then do the mapping. But then there's also the problem of finding the appropriate kernel function. So I'm not explaining that, but that also itself is a bit of try and error and then work. But so here you go. So that's what kernel PCA is attempted to do. And then instead you notice this inner product. And then instead that you actually represent this parts using kernels. And then you could actually, so the benefit of doing this is that you could still apply this eigenvalue decomposition problem and to get that eigenvectors. So kernel version of principal components, right? So you can find it. Okay, so you want to see how this works, right? In the solar wind case, I'm going to come back to solar wind example. And then, so I found this paper by George Amaya, 2020, in the Frontiers. And then I'm basically this is a really nice paper too. Okay, and then I mean, I'm just showcasing a few convenient examples that I found in this paper to fit into today's lecture. But it's about so it's again about classifying solar wind data and then applying data sets used in this paper is a 14 years of ACE data set. So it's basically quite a bit of overlap. So I'm just going to explain this first. So solar wind classification decision boundaries being learned from 14 years of ACE data sets. And then, use collection of PCA, clustering, and then Gaussian mixture model, which you learned, right? Okay. And then, so here instead, 7 feature space. Sorry, it was 9 feature space. Instead, it's used 15 feature space. So there are additional solar wind features, parametric features that introduced. And those are again based on experts understanding or analysis of solar wind without using machine learning. So those are the sort of, this is the list of 15 features. So this is the raw feature space. I'm emphasizing you don't need to do clustering just using this 15. So that is Amaya's suggestion, or like to deal with this problem that you actually highlighted, that coming from about this nonlinear distribution, data that distributed in a nonlinear way here. Okay, so I'm going to show a few examples, but what's happening in this paper is that, so it's go from right to left. So just to give you a context, right? So you get the bag of data, right? And then the example that I explained just before, the hydrogen and Miesner's, so that's hyphenated. So that's work that it's in a textbook, went from data sets directly to k-means, right? Yeah, so that's what I explained. Here in this paper, it's going, for example, through this KPCA, kernel version of PCA. So doing a feature engineering. Instead, for example, like using, I said that 15 features, right? You could do the clustering using raw feature space, using raw features, but you could do, in this case, KPCA, or maybe just PCA, or other type of maybe pattern recognition methods to do the feature engineering, right? And then do the clustering. Well, and then you could do that Gaussian mixture version. And then there's other example that highlighted in the paper. So they're comparing different methods in this paper. Yeah, okay, understand the context? Okay, so then I'm gonna show this. So I'm cherry picking results from this paper, right? So there, left-hand side is PCA results, right? So well, feature in just a pure PCA application to the solar wind. And then so what it's doing is that, so this is a 15 space, 15 features. So how many principal components could be found? Okay, 15. So that's so it's just showing like a 4 here. Well, it's just showing a C1, C8, and then C. So that is a phase space, right? Does that make sense? So just this paper only show the C1, C8, and then here kernel PCA results, and then C1 and then C2. So these are different components, principal components found different applications, yeah. And then the original solar wind data sets. Solar wind data sets get projected into this particular, well, so four different categories of solar wind that the expert knowledge classified by Zhu and Bolosky. So they use 4 solar wind categories. So CH is red here, right? So this is actually fast solar wind of corner hole origin. So those are experts said these are the things, and then it get projected onto particular PCA or PCA space. Does that make sense? This is a way you can visualize your PCA results. Does that make sense? Are you okay? So you're nodding. There are a few notes. Thank you. So I'll proceed. So like you can see, what you see here is purple. Is this is a TL transients, ejector, and then CME type of thing, and then get projected this way in C1, C8 space like this. But look at this KPCA. It's a bit of overlap, right? And then SR is a solar wind of sector reversal region. Okay, so there's a bit of overlap, but if you do KPCA, that's a bit separated better. So that's answer to your question. So KPCA might be a way to separate these data sets a bit better. Physically, the map to physically interpretable samples. So this is one small example that I could find, and then maybe you're gonna do better, right? Okay, so but that you don't need to just do the so this is a projection. So then on top of it, there's a clustering done. So K is chosen to be 5, and then so you can see there's 5 distinct colors. So and then so instead using raw features. So this one is raw features. So the 15 raw features are used in conjunction with the k-means, and then it's been visualized. It's been projected onto this space. I'm sorry. Okay. And then here is a k-means plus KPCA, and I can see that this is a different implementation. So this is a k-means, and the bottom right is Gaussian mixture. You can see, I don't know, like it's a bit better separation. So you combining feature engineering and then especially KPCA in this example, you could get the better outcome, where the data are clustered in a way that maybe map to more, it's clearly separable groups. Okay, so this is one example. And there are a lot more in this paper, so I encourage you to read. Did it, okay? Maybe I'll stop here because I'm gonna jump to a different topic. Next, and I have to check the time, but I think I'm okay. Okay, who have microphone? 25 minutes, okay, cool. Question up, yeah.
Just a quick clarifying question. So was the kernel here chosen by the authors, or was it in a way inferred during the process?
So in kernel is chosen by the author.
Okay, so they picked some variables that they thought, okay.
Yeah, so that's yet another difficult part about picking kernel. Have you used kernel method? I mean, vector machine.
Not yet, but I can see how it's useful, but you have to be very careful.
Really, that's sort of but better than solving the original problem. Good. Okay, go ahead. You have to throw. Can you go?
So I already asked this question from Farzad, but still I gonna repeat it again. So if I know that there are some small amount of very interesting events to me that I would like to separate in a different cluster, and this number of events is small comparing to, say, other types of events that we could observe. Does k-means work well with that, or maybe I can weight these events somehow, maybe on some physical parameters?
Okay, so your question is that you have some intention, well, you really want to identify a group that tend to be smaller number of samples?
Yeah.
Okay.
So we know, for example, let's assume that solar wind is mostly stable and there are some very interesting events where some change rapidly happens, but it happens very rarely. How can I deal with that using k-means? Should I use something else, or maybe I can somehow weight these events, I don't know, based on some energy or some other physical property?
So some people do sort of data thinning or data selection. I guess that's probably first thing people might do. So basically, you want to really smaller event numbers, but transient, dynamic, sort of part of solar wind, and then I do it like in my research. I really want to identify some mode of field and currents that associate with substorms. But then most of the time it's quiet. Magnetosphere is most of the time quiet. So if I do clustering or any kinds of supervised methods, overwhelmed by this majority of decision rule or PCA even, they pick up the nominal mode. But then it's So I could digress, go on, because that is so number one, good question, and that is a real problem. Right, like because we really want to focus on dynamic time. That is the time that we want to predict, right? And that number of samples small. Okay, so I'm congratulate you in understanding this. It's a real problem. So one thing to counter that is even before going to k-means sum up and sum down, usually people do like a sort of data balancing in the machine learning. So like you just make sure that balance the data. So you basically thin data. Like you don't need like slow solar wind because that's kind of predominant category of solar wind. And I actually do that for myself too. So that balance the data sets before feeding to any kinds of machine learning. So that's good practice. Second, so after that, there's definitely one method works better for your specific purpose. The conclusion of this paper is basically, if you use different clustering methods, you get different results. So I will, like I'm more so that's that. So balance the data or send the data, right? And then try out different methods and see how that works for you, for your purpose. So I think it's just the trade-off, right? It might get easier now to try out different methods, but what you are asked to do is try many different things, right? Well, because it's easier, we expect that you just don't present k-means cluster as a final answer. And then you also could try out feature engineering. That is a important step. I don't know, I could go on. Maybe we have a similar questions. Good, okay. Anna?
I have a little different question. So you go to KPCA, if there are any non-linear features in your data. So my question is, when you go to a higher dimension, how do you identify that that particular higher dimension is non-degenerate? And how do you ensure that the kernel matrix that you obtain is unique?
Okay, so I would say it's non-unique. Definitely non-unique.
Thank you.
So then in this PCA case, you could just look at that, how, for example, if your goal is to efficiently devise segmentation application, for example, you could see like a number of principal components. If you use PCA, you probably need a higher number of components to describe same number of variants in the original data sets. But KPC, probably you could use less number of components to describe similar number of variants. So for example, you could compare, and then choice of kernel could be used that way too. Like what is the most effective kernel that give you advantage of explaining more variants with fewer number of components. That's your goal. Yeah. Yeah. So those are really good questions. Looks you're thinking about this. Okay. Good. Okay. So before Nick stand up and then kick me off from here. And then, so I want to kind of change a bit of topic, and then also get to the research that closer to myself. And then I'm going to use ionosphere, thermosphere application examples. And then I'm going to explain a bit of PCA. But so as you have seen in a couple of slides ago, that you basically what's happening in a like a conventional PCA algorithm is that software level it's computing a sample error covariance and then doing an eigenvalue decomposition. So this is my so this is a dilemma that I personally encountered. When I was a graduate student, my advisor gave me a big bag of data that, that D2 that he really liked to analyze, and then I was given. And I was analyzing, and it was so hard because it goes like this. So the satellite go over the polar region, so one satellite transect. So 1.5 years of data sets, but it's still like, oh my goodness, it's so sparse. Imagine this is the same as a magnetosphere anywhere solar wind. We have so little data sets given that massive space that we want to understand. What I end up doing after year or after the trial and error, so went back to PCA analysis, but had to look at the original sort of the theory behind the PCA. So I think you learned this, that there's a Kaplan lobe expansion is basically the foundation of PCA decomposition. So what you could see, the PCA is that what you have learned is a discrete version of Kafunen law of expansion. So what it does, what it's saying is that any stochastic process, basically random parts of the data sets, can be expanded to the sequence of independent random variables that basically projected to orthogonal basis. So this is just a definition. And then you could do it without loss of information, which you see the integral go infinite, right? So this is a Kafunen law of expansion. So I was encountered to apply PCA, but my data are sparse. And then now the reason why I'm sharing this story is that, okay, you start 10 days, most of the time that you have to stare at those equations, right? So this is so if you understand what the PCA is about, what the actually theory behind it, I've been telling you, it gives you edge. So this is the one example. So you can see the original Kafunen law of expansion shown here, right? And then it's basically expanding onto the orthogonal basis, the random data set. And then when you actually think about it, this is what I want. So I went back and then look at the expansion and the top equations, and dot means, I want them to do it to the infinite number of bases, but that's what's happening, right? Okay, I want to decompose my data set, project to the orthogonal basis. And then what I'm doing is, I am actually if you look at the alpha, that is basically, in this case, I was looking at DE2 data sets. Those are time-dependent coefficients that original DE2 electric field data set get expand to the orthogonal basis, right? And then what I wanted is that basically here, this one, middle part, this is basically covariance of the coefficients of the orthogonal basis expansion, right? So that is basically, this is a covariance, right? That's, I don't have covariance, right? But that is what's happening. So that's a realization. So you write it down to the original interpretation of mathematical interpretation of what the PCA is about, and then write it down, and then think about it. Oh, the number one, direct estimation of psi and then lambda directly from sparse data set was infeasible. So what can I do? So I end up introducing yet another basis. It happened to be spherical harmonics, and then project that describe that psi in terms of yet another orthogonal basis, basically introducing constraints into this problem. And then so once you rewrite the problem that way, then I know I'm skipping over the details, but then this problem of PCA decomposition become estimation of alpha and then beta. This is the spherical harmonic coefficient expansion, and then I have to make sure that this beta is actually orthogonal to each other. So you could do it something called QR method. So yet another method, but you could do things like that. So I'm just gonna skip over, but here the lesson is that if you understand that, so if you get stuck, go back to the textbook, go back to the notes you have taken this week, right? And then think about it. What am I doing here? Huh? Then you might get this, yes, right? You can do it, right? So it's really important. It's a convenient time. The speed is essence time, but also, that is where you can actually intellectually contribute to this endeavor, right? And then, so this is the result. So expand it, and I'm just showing results in the form of, these are you just showing the principal components in the form of electrostatic potential, because I have spherical harmonics and a bit as a sort of basis. I could do that. So you can see the E.5 of DE2 data set tell the those data sets can get expanded onto, in this case, I only estimated up to 11 because and then you can see that variance explained in the data set goes. So each component explain a different amount of variance, and then it goes down, right? And then as you increase that number of principal components, and you can see some of them are here in my coupling person, you could see that, oh, this is a BY effect. And I took a correlation between those alpha, the time-dependent coefficients, and then solar wind, and then correlated. And then, so that's a way that I could show the interpretation of each moment, each component. Okay, so that's a long time ago. And then I didn't really think that this is that useful, but it's after graduating, so other people found this useful. So this is done by cousins as well. And then she was postdoc at the HAO a long time ago. And then she applied to Superdant data sets and then found similar results. Superdant, just nature of instrumentation technique is a bit noisy, so variance explain is lower, but found that different interesting results. And then, so just gonna press ahead. Well, and then also later on, I was also found myself in a similar dilemma, and I was given yet another bag of data as well, the CHAMP, I don't know if you know, but mass CHAMP is actually the satellite mission that it's a carried very accurate accelerometer. From that can measure mass density of the atmosphere. But also, like, satellites, I'm just showing a transect here. So it takes about 19 minutes in a low Earth orbit, the satellite going around the Earth. So this is an open circle here shown. And so every 90 minutes, the CHAMP samples the atmosphere, and that's really sparse. What we wanted to understand is global changes of mass density, right? So it's you could definitely accumulate, 9 years of data and then get the mean, but I wanted to understand the mode of variability, for example. So I found this method that we used when I was a PhD student, and I applied to CHAMP. So you can see the color is awful on the screen, but so you can see that decompose. The PCA has a different name. It's called empirical orthogonal function. So PCA component 1, 2, 3, 4, 1, 2, 3, 4, right? And then variance goes down as you increase the as it was increasing mode, higher mode of principal components. So if you remember the previous slide, EOF1 distribution look very similar to the mean distribution of mass density, basically driven by the solar UV, right? Day side has a very higher density because temperature goes up. So it's just really simple distribution. But when you see the PC2, PC3, and PC4, it gets more complicated. Usually, that's kind of happen. It's smaller scale features get picked up by higher order principal components. So as I said in the starting slide, what we're doing is not just, we want to understand the data. We want to create the knowledge out of this data set. So then not just the PCA, but then doing a bit more, right? So then in a 2-3 slides ago, so I showed that there is a time-dependent coefficients that you can project it, or you can fit to the principal component. So 9 years of data. So I have 9 years time series of coefficients that project, coefficients of each EOF mode. So you can see that, clear solar cycle dependence that is shown on leftmost plot, right? So you're looking at that coefficients, and then EOF2 look like there's one stronger feature in the northern hemisphere and the southern hemisphere that happen to be seasonal mode. So by analyzing coefficients, that you basically back project Once you get the principal component, you project back and then look at that coefficient. Then you could actually, that will help you to interpret each different modes, right? So that's what's going on. And then you could, for example, what we did is that we did the periodogram, so you could do the wave decomposition of those time-dependent coefficients. And then what we found is that there's 9-day oscillation. So that is related to co-rotating high-speed stream. So these are really data-driven discovery. So so by combining different methods, you could get you can actually extract knowledge out of data sets. So those are example. And then I get to the last few slides. So to summarize, thank you for paying attention. And then unsupervised machine learning techniques are useful, regardless of your end game, right? Like you want to do more fancy stuff, do it because it's a low bar, right? So it helps you to examine and understand the data set a bit better. And then I would put that in the back pockets, and then no matter what, right? And then so if your goal is to reduce the number of data size, it's a really powerful PCA, KPCA will reduce dimensional reduction methods, and then really powerful method to extract the patterns, right? And then and the clustering. Right, and so let data tell us how solar wind are clustered, rather than you say, I want to see this CME. No. Let data tell you, right? That is it's a hard thing. It's hard. Actually, it's hard because we want to see what we want to see, and then often you see something you are not expecting, and then you have to be curious. So, but you're at a really good starting point. So are you ready for your data-driven heliophysics science discovery? Raise your hand. Yeah! Good. Congratulations. And then those are references. I took most of materials from those books and then papers. And then these are posted on our website. And then congratulations. You're doing great.
Thank you for a wonderful talk. So I understand that if we have 3 dimensions of components, so there will be 3 components, right, from PCA. So suppose I want to know maximum variance, intermediate variance, and minimum variance, but my 2 components have degeneracy. So one of the this question is related to the question asked earlier. But I want to know how to resolve this degeneracy in these 3 components. I want PC should give me some result so that it should resolve this degeneracy. How to do that?
So you have specific application on your mind.
Yeah.
So you apply PCA to some data set.
Yeah.
And then you end up seeing 3 components that explain quite a bit of variance. Yeah?
Yes.
And then you want some physical processes to be separated conveniently by these 3 components. But you didn't see it.
Yes, because of degeneracy.
You don't see it.
Yeah.
Difficult part is that unless we have infinite amount of data, we won't get that. I mean, that's so my practice. I practice this a lot, and like my students, they get backup data because I don't have time, right? But it's so hard. so hard to really, I don't know, like, so the truth is that data is telling the truth. Data's truth, right?
Yes.
So it's actually what you think that physically distinguishable. You know, you think that those processes should have distinguishable outcome in the basically features that you're looking at. So maybe you need to, that's not distinguishable, right? It's mapped to the same PC, two processes, right? And then like one, so that is a sort of humble truth about data you have. But that, yeah, and then like so you could see by increasing features, right? Maybe get mapped to different, maybe, you know, you find a different components, and then now you learn about KPCA. It has its own challenge of choice of kernels function, but if you haven't tried that, I would, right? And then there are other sort of, you know, class of dimensional reduction methods out there. But also that is typical.
So just to maybe a naive question to ask, like how much error it will introduce then in my results?
How much effort you should
Error.
errors. How much errors?
Ah.
What? Could you complete this?
How much error it will introduce in my results if I am not able to resolve degeneracy? Can we quantify it? Like I don't know if we quantify or not.
So it's a, so one way is, so one metrics of success of, you know, pattern recognition is a smaller number of components and a maximum amount of variance explained, right? So that's one clear metric. And then, but then you are actually have different objective. You want particular process to be projected to some components, and then so that's a science goal, right? So it's really hard to put that, you know, like what you're saying, how much error you should tolerate, you know. So I think it's also like step back and then like go back and then like maybe just do clustering of data, maybe because, you know, there's a question earlier, right? Maybe data are not balanced. It's hard. I'm sympathetic to you. I mean, I am. I love data analysis, but it's hard.
So maybe I didn't understand the kernel transformation well enough, but my question is like, how do you ensure that when you do kernel PCA, that the kernel you apply doesn't introduce clusters into your data set, particularly in like high dimensional space when you don't know what to expect in terms of the clustering?
But so I happen to present this a combination of KPCA and then clustering, but those are two different methods that could be, right? So your question is, so how do we know that KPCA inadvertently introduce some sort of error in clustering? So clustering itself, clustering is an end goal, right? Clustering has its own objective metric, which is within, you know, basically minimizing within a cluster variation, right? So I would look at the loss function. If you try out, oh, I found a cool kernel and then I tried and then did the whole thing and then like made things worse. That is empirical, but there's objective function for the clustering. If your goal is clustering. So it's really, you know, you get bogged down into, I get bogged down to like, you know, but then you kind of have to kind of see the whole thing, what your final goal is. and then go back to definition of that method. Don't get stuck at the software level. Go crazy. Just open notes and then, what am I doing? And then you get that answer. So like summer like this is really it pays off, I think. I think it's lunch time or not? Okay.
More questions for Tomoko or
Yes. Are you gonna feed me lunch?
Yes.
Okay.
You have to talk to the students. So
Oh. Okay. I see.
Thank you. Okay, this is a broad question, but like sometimes we don't know what the correct X to fit into PCA or KPCA for clustering. Like for example, if you only fit in velocity field and magnetic field, machine learning may not recognize a good enough pattern as compared to if you fit in like V dot B, like cross.
I know.
cross
So that you were asking.
And so I was wondering if there are algorithms of finding good enough kernel to recognize the underlying patterns in the data themselves before doing clustering or before doing.
Yeah. Okay. So. Right. So I think so I think there are two questions. Sounds like one is about feature engineering and then feature selections.
Yes,
right?
so one is about selection. Machine learning can recognize pattern in the data before doing the clustering, and the other is could finding the right kernel be a solution to that?
Yeah. Again, kernel is powerful here if it works, but it's really difficult. So here in this paper, it's a paper has something called a visualization unsupervised method or something, and that's really again we have. Do you know that our brain, most of frontal cortex is a visual, dedicated to visual. I don't know, understanding of the world. So you have great computer in your hand. So visualization to me it's really important. So once you do PCA, and then so again I think this paper used 15 raw features, right? And then like those are kind of like chosen not by data, but then sort of. So you could add more features and then might get the better results. Better results means that, for example, in this case, this is a physically interpretability of clustering, or not clustering, but the projection. So here, for example, so you went back to the 4 different categories of solar wind proposed by Ju and then Shu and then Brodsky, right? So you can see the goal is that if those dots are separated by different subspaces, so that's one way, right? Like, is it working the way you want? So I'm answering that, like you asked, how do I know, right? One way, how do I know that your PCA, KPCA is working or not?
I think my question is, how do we know this is the best way of, like?
So then, what is your best, right? So like previous students said, I want to separate particular physical processes into different components. That is your definition of the best, right? So what is the definition of your best, or get you, So then it's so again the lesson at this point is that there's no such thing like the best, definitely unsupervised method, right? So you're gonna try out, and then but keep your goal really clear, because I could get lost when, with students, and I get lost, like, okay, interesting results, but then you have to really keep like, what am I doing? What am I doing? What this method is doing? What I want scientifically, and then because it's speed of analysis is so fast, you can get lots of different results, and then you get overwhelmed or get lost, right? So I think it's in some sense, you are the captain of your data analysis endeavor. And but then also, so like even if you really want to separate these physical processes into different modes, you just have to be honest with what data is telling you too, right? If you really, you have to make sure that you implement it right and all that, right? But then you got to kind of like be curious what data is telling you, because that is where you might actually see, you might be the cusp of discovery, right? So I wouldn't sign off like the analysis results that, that, okay, it didn't give me what I wanted, but maybe you're onto something else. I'm sending back, question back to you. It's up to you. Yeah. Your advice, I wouldn't know. Okay.
So I'm just looking at your paper with PCA. Yes, my question is more the question of empirical orthogonal functions. So PCA by itself is a linear method.
Right, linear.
So does this sort of additional coefficients from empirical orthogonal functions? So my worry is what if I do this sort of PCA, find main components, and then somehow, because they have just linear multipliers in front of them, they will sort of, for example, for your case, somehow widen the region of this drift. That will be unrealistic. So is empirical orthogonal functions this additional term that you multiply with somehow fixes that, or it's still a concern?
So I mean, empirical orthogonal function is a basically PCA. It's the same, right? And then maybe I need to understand what you're saying. So we did something that we knew that some of the data sets have errors, so we introduced some error terms and a loss function. So it wasn't really straight PCA. If you go back to Kafunen Love, there's a same, right? Like you can implement it as eigenvalue decomposition and sample error covariance. The work I had to do as a graduate student, because that was not possible. So I did totally different way of getting it. And then, but then, if you go back, it goes back to the same principles. But then again, methodology was, you were asking end up getting the sort of imperfect decomposition because I was dealing with data with errors, uncertainty, that's unquantified usually, right? And then also, I mean, it's I had to cut off because it's sequentially estimated from PC1, PC2. So it's a different approach. So where to stop? So I didn't really have clear sort of elbow curve that composite people say. Like I couldn't really do that either. Where to cut off? So there's a flaws, but it's imperfect, but it's better than that. I don't know why so definitely I didn't understand that your question. Is that linear decomposition? Yes, it is, because that's what this sort of definition of the method is. But there's a noise, so it's not perfect linearly. It's not perfect decomposition if you look at the individual data sets.
You partially answered it with how many orthogonal functions you need to use. So.
Oh yeah, that's unanswered. And then that's funny because not funny, but then so there's I could share the one paper by Joe Knowles who have looked at this problem. that the basically well identifiability of eigenvalues. So eigenvalues, basically precision of eigenvalues, like right, like how well you are actually determined, and then how many you should actually is identified, can be identified given the noise of original data sets. So there's a way to sort of, I don't know if I'm answering your question, but how many bases, how many components you should get, or components you get is well quantified given the error of the original data set. So there's a question like that, and then there was one paper from 80s that I mean really try to address that question.
If you could share it, that would be great.
Yeah. I mean, it's empirical, right? Like the name suggests. So it's you just try to always do better than nothing, right? Like that's you are sorry, you are scholars, right? You are presenting scholarly argument. You're not saying that I did it. It's better than other methods because of X, Y, Z. Right? You could build arguments, and that's how we make progress, right? Look at what changed from the time I was a PhD student, right? Imagine when you are standing here, so, right? So, but then it's important that you make progress. You carry that into the future. Thank you. Really good question.